Structured data, like the familiar rows and columns you see in a spreadsheet, is the absolute foundation of modern data science. But to feed this raw information into advanced algorithms, we need a reliable translator. Pandas acts as this essential bridge, taking messy raw information and elegantly preparing it for a complex AI models. You might wonder how this fits in with other Python tools you've heard of. While a library like NumPy is brilliant as a high-powered calculator specifically for numerical arrays, Pandas operates much more like an automated spreadsheet. It gives you that familiar tabular layout, but with the added superpowers of extreme speed and automation. Let's bring this to life with a real-world scenario. Consider a bank manager at HDFC Bank. Every single day, they might receive a massive file containing 1 million customer transactions. Imagine trying to manually open that in Excel and filter it, finding customers who are spending over 50,000 rupees, or calculating aggregate balances across an entire city, or manually fixing missing contact details. It is incredibly time-consuming and heavily prone to human error. But Pandas steps in as your tireless automated assistant. By writing just a few single lines of code, you can process all those millions of data points in literal milliseconds. This level of efficiency transforms data handling from a painful manual chore into a streamlined, highly reliable programmatic process. To actually harness this power, we need to understand the architecture. It's built upon two fundamental building blocks that you will use in almost every data task. First, we have the series. Think of a series as exactly what it looks like, a single column of data. It is a simple one-dimensional array. Notice how every value in this column, like Alice, Bob, or Charlie, has an index label right next to it, essentially giving every piece of data a specific home address. Then we have the data frame. A data frame is the complete two-dimensional table. If you look closely, it is really just multiple series aligned side by side. We have our column for names, but now it's grouped with age, city, and salary, all neatly organized into rows and columns. To make this stick, use this simple visual analogy. A series is just a single strand of thread representing one specific attribute. But when you weave those individual strands together, the data frame becomes the entire complex fabric that holds your complete data set. So your core takeaway here is that Pandas bridges the gap to advanced data analysis by turning messy data into easily woven, manageable tables using series and data frames. Now that we know how this data is structured, let's look at the specific commands we use to manipulate it. Let's dive right into how Pandas actually manipulates these data structures. Here on the left side of the screen, we have a list of the most frequent Pandas commands you'll use in data analysis. Starting from the top, read CSV is your starting point. It's how you load external data files into Python. Once your data is loaded, head gives you a quick sanity check by displaying just the first 5 rows so you can see what it looks like. Next, info tells you the structure of the data, showing you what columns exist and what data types they hold. When you need to understand the numbers, describe instantly generates basic statistics like minimum, maximum, and average values. If you want to grab specific pieces of data, lock and ilock select specific rows. You use ilock to find data by its numerical position, while lock uses specific labels. To organize your data, GroupBy is a powerful tool for grouping and summarizing, like calculating total sales per region. FillNA is incredibly helpful because it lets you fix missing values or empty cells. And finally, merge lets you join two separate tables together, operating much like a join command in SQL. Basically, these operations allow you to seamlessly move from a raw file through exploration and cleaning all the way to finalized insights. To really understand this, let's look at a concrete data structure. Down here, we have a sample hotel booking register. In Pandas, each horizontal row is an observation, meaning it represents one specific entity. For instance, this first row is a single observation detailing Raj Sharma's stay in room 101.
On the other hand, each vertical column represents a feature or attribute. So if we look at the city column, it gives us that specific attribute for every guest. Now take a look at the entry for John D. In his stay column, we see the letters NaN. This stands for not a number. It represents a missing value, likely because the duration of his stay was just never recorded. Thankfully, Pandas provides built-in tools to handle exactly these kinds of messy realities. It lets you instantly find those missing gaps, filter out specific guests, and summarize large numbers like the total bill instantly. Next, we'll see how companies process massive data sets using these exact tools to speed up their daily operations.
To see how these pandas commands actually play out in the real world, let's explore a couple of powerful examples from completely different industries. First, let's look at the banking, financial services and insurance sector. Take SBI credit cards for instance. Their fraud detection teams are tasked with processing massive CSV files every single day. Using pandas, they can take a single file containing 500,000 transactions and load that raw data into their system in a matter of seconds. Once the data is loaded, they quickly apply a filter to isolate the high-value transactions, specifically any transaction over 1 lakh rupees. Then, they take those filtered results and merge that data with a known list of blacklisted merchants to catch potential fraud before it escalates. Before using Pandas, this entire workflow was a grueling manual process that took about 4 hours to complete. But now, the exact same analysis is a lightning-fast process taking less than 30 seconds. Now let's switch gears and look at an e-commerce scenario. Flipkart's sales analysis team relies heavily on Pandas during massive high-traffic events like their Big Billion Days. You're dealing with enormous scale of information, often processing well over 10 million rows of product sales data. By using the command GroupBy they can rapidly aggregate all that information and identify exactly which product categories are selling the fastest. Next, they use the merge command to combine these live sales numbers directly with their current inventory levels. This allows them to calculate a crucial metric, sales velocity. By constantly checking if the sales velocity is greater than the stock remaining, they can accurately anticipate shortages. When a product is about to run out, the system can automatically trigger an alert for the warehouse to restock those items. Complex supply chain processes like these, which would normally take a week to perform manually, are now completed effortlessly in just minutes. By leveraging these robust data tools, organizations can transform overwhelming floods of raw data into actionable insights instantly. Next, we will step into the Python environment and see exactly how to write the code that makes this powerful analysis possible. Now that we've seen how large teams handle massive data, let's walk through exactly how you implement this in Python using Pandas. First, we need to create a data frame. Data usually starts out in Python as a simple dictionary, where we have keys like order ID and city paired up with their corresponding lists of data. To turn this raw dictionary into a structured, readable format, we use the pd.dataframe command. This takes your dictionary and automatically converts it into a clean row and column table that's much easier to work with. Once we have our table, we move to basic exploration. You rarely want to print a million rows to your screen, so df.head3 gives you just a quick peek at the top 3 rows. To understand the actual size of your dataset, df.shape will return the exact dimensions, telling you the number of rows and columns. If you need to verify what kind of data you are dealing with, like text versus numbers, df.info reveals all the data types. And for an instant mathematical overview, df.describe provides a statistical summary, calculating things like the mean and the range for all your numerical columns. Next, we have selecting data. When you want to isolate specific information, you simply pass the column name like customer name inside brackets. That pulls out just a single column. If you need to analyze multiple features together, you pass a list of names inside those brackets, giving you multiple columns side by side. Sometimes you just want a specific row based on its position. In that case,
iLog2 reaches in and retrieves exactly the third row. But what if you only want rows that meet a certain condition? That's where filtering rows acts like a search engine. The syntax dfcity equal to Mumbai instructs Pandas to filter the table and keep only the rows matching Mumbai. You can even get more specific by combining conditions with an ampersand symbol, meaning you can pull out rows that are in Mumbai and belong to the electronics category at the exact same time. In real-world scenarios, your data will have gaps, which brings us to handling missing values. First, we count how many blanks we have using df.isNull.sum. Now, deleting rows with missing data is dangerous because you lose valuable information. A better approach is to calculate the average or mean of that specific column. Then, you use the fillNA method to replace the missing NaN values with this average, safely maintaining the integrity of your dataset. Pandas also makes adding a new column incredibly fast by doing math across entire columns at once. If you need to calculate an 18% GST for every order, you just take the order value column and multiply it by 0.18. By assigning this to df.gst 18%, you instantly generate a new attribute for every single row in your table. When it's time for deeper analysis, GroupBy is your ultimate summarization tool. It clusters similar rows together. For instance, df.groupByCity groups all your orders by city and then attaching .sum adds up the order values for each of those groups. This transforms thousands of rows into a clear summary of total sales by city, perfect for feeding into bar charts or pie charts. To make those summaries readable, you use sorting data. Calling sort values with ascending equal to false organizes your list so that the highest values appear right at the top. Finally, after all this cleaning and analyzing, you need to save your results by exporting data. The toCSV command takes your finished table and saves it as a new file, which can easily be opened as a CSV or shared as an Excel file with your colleagues. By mastering these 9 steps, you build a complete pipeline that transforms scattered information into actionable insights. Let's see how these exact same concepts help a manager at Tata Motors spot manufacturing risks instantly.
To see how these concepts come together, let's look at a manufacturing quality control scenario at Tata Motors. When provided with a dataset containing parts, plants, and defect rates, our main goal is to systematically identify risks. In this scenario, we need to calculate a new column called defective units. We do this by taking the defect rate and multiplying it by units made. This straightforward equation translates an abstract percentage into a physical count of broken parts. You can see the results in this newly added column on the right side of our table. Next, we filter our data for a defect rate higher than 0.10. By applying this filter, a manager can easily isolate the high-risk components, completely removing everything that doesn't meet that critical threshold. After filtering, grouping by plant reveals which specific location requires intervention. If we look at this resulting bar chart, we can clearly see that plant A has a significantly higher total of defective units, indicating it needs our immediate attention. Now, looking down at step 5, you might wonder why we prioritize certain data cleaning operations. Why use the fillNA command instead of just deleting missing data? Think about critical industries like healthcare. Deleting a patient record entirely simply because one field is missing could lead to dangerous gaps in medical history. That's why filling the missing data safely is so incredibly important. It preserves the integrity of your dataset. This entire logical flow, from loading data and cleaning it, to filtering, grouping, and identifying risks, culminates perfectly when we export our results. Mastering these core operations allows you to handle 90% of real-world data tasks. You now have the power to transform massive, messy datasets into clear, actionable insights in just a fraction of the time it would take using manual tools like spreadsheets. Ultimately, you are no longer just viewing data.
you are controlling it to drive informed decision making in any industry. If you remember one thing from this entire process, it's that combining these simple foundational data operations gives you complete, robust control over extracting real value from raw data.